It's not very comfortable, but anyway. Okay, this talk is about semi-classical spin hydrodynamics, and I mean we have different flavors of spin hydrodynamics now. Do you hear me well? And semi-classical spin hydrodynamics is the name that I suggested for the formalism that was developed in Frankfurt by different people, particularly by Nora. Then it was carried forward by David here, and he brought it to Florence, which is a bold move. And then he restomed it here, and then Sushan put it on a computer, and he has some nice results. He will be discussing it at some point in this workshop. And also, this is going to be extended by Anna Maria for her doctoral research work. And I think the motivation is quite clear to all of us in this room that we have in non-central collisions, we have large initial angular momentum, which is partially inherited by the fireball, and finally, according to conservation of angular momentum, it is going to be detected as polarization of final hadrons, and in particular Land-Diprons, because they are quite easier for the experimentalists to measure. But the thing here is that everything is about, I mean, relatively, yeah, it is in this. Uh, the the point here is that everything here is based on the very concept of conservation of angular momentum. And this is exactly the agenda of spin hydrodynamics, to take angular momentum as a separate conserved charge and add it to the standard hydrodynamics. And I mean, the equations of spin hydrodynamics are usually written in this form. You have energy momentum conservation, you have angular momentum conservation. And this guy, the J, this can be decomposed into an orbital part and a spin part. And the definition of the orbital part is given usually by this. And then, okay, you will have a nightmare. The god of covariance will come after you, because this means that you are writing something that is not only valid in the flat space-time, but also it is tied to Cartesian coordinates. So the first question that some geometrically trained mind would ask is that, does it mean that you can only use spin hydrodynamics in Cartesian coordinates? And just to recap, there is actually an easy way to define orbital angular momentum using symmetries of space-time, which is you have a Killing vector which generates rotation. So it satisfies the Killing condition, and then you contract it with a. So now the metric is sorry, the tensor energy momentum tensor is assumed to be symmetric. So if you contract this guy with this guy, and then take the divergence, okay, then you will end up with this relation, which gives you the thing that this has zero divergence. And this means that if you integrate over this guy, this R is an index of that counts the Killing vectors. If you integrate over an arbitrary Cauchy hypersurface, of course, this is not a very beautiful picture, and then use the divergence or Gauss theorem, that this means that this integral, which is the total angular momentum, remains the same during the evolution. Now the question is that what if the energy momentum tensor is not symmetric? So basically, then you will have an anti-symmetric part multiplied by the anti-symmetric part of the gradients of the Killing vector. And this guy is not zero, of course. And now this guy is not conserved anymore. So what can we do? First of all, we can use this equation, which I would call it spin dynamics postulate, that says that, okay, the anti-symmetric part of T mu nu is given by um, the divergence of S lambda mu nu, the spin tensor. Sorry, there is a minus sign here. And this guy is a covariant derivative again, like this covariant derivative. And then you also use the fact that in flat space-time, the second order gradient of a Killing vector vanishes. With that, you'll find the correct form of the conserved charge current as this. So you have a T mu nu contracted with the Killing vector, and then you have this uh, this spin tensor contracted with the uh, with the gradient of k. And then you will have a covariant decomposition of the total angular momentum. The first part is the spin angular momentum, given like this. And then you have the orbital angular momentum defined by this. So it means that you're safe, then you can use any kind of coordinate system that you want to use. Okay, and there is a sanity check you can do in the rank 3 tensor definition. We had 24 degrees of freedom because it was anti-symmetric in the last two indices. And the number of Killing vectors in the flat space-time that do not have a vanishing anti-symmetric gradient is also 6. You have 3 generators for boost, and you have 3 generators of rotations. All of them make, each of them make a freedom, so the number of degrees of freedom is the same. Or if you're still worried about these definitions, you can check our Appendix A in the paper with Ana Maria that we have made explicit calculation showing that actually these two definitions coincide in the case of Cartesian coordinates. And then when I was in Trento, and Amos showed me what is going, what happens using the variational approach for the energy momentum conservation, I thought about, okay, how we can extend this definition to curved space-time. And the main problem or main novelty is that then the second order gradient of k will produce a Riemann tensor here. So then you can write this, you take the divergence again, and you will end up with these two parts. And you can assume, okay, I want to postulate that the divergence of the total angular momentum, as I have defined before, vanishes. And this gives me these two equations. And these are exactly the equations that you find from the variational approach. And so it means that this definition is actually a definition that works in that approach too. So this also resembles the Joule heating term on the other side. So you have a kind of source term, and of course, if you go to use the Belifante gauge, that S vanishes, and if you believe that Belifante and Hilbert tensor are the same, so you will end up with T mu nu being conserved. And yeah, as I said, this agrees with the variational approaches that are taken by Hill back in the days and also by these people. No, yeah, it's no longer zero. In arbitrary pseudo gauge. Yes. Yes, the Belifante still has. No, it doesn't have anything to do with not having general relativity, because when you find the Einstein equation, you use the Hilbert definition for T mu. Yeah. So no, it's exact. No, it's just. I mean, no. Sorry, I lost everything. Mm. So you can. Yeah, it doesn't need. Yeah, exactly. Yeah, exactly. This. Yeah, yeah. So you can put. So, go on. I mean, if you have a canonical, for example, T mu nu. Yeah, yeah. Yeah, exactly. These are the only equations that you can write that are pseudo-gauge invariant. Otherwise, if you write, if this term doesn't exist, this modification doesn't exist, you will end up with some. You will end up with believing that there is only one correct pseudo-gauge. Yeah, let me show it. Yeah, exactly what I want to show now. Okay, so you have, I mean, there is the pseudo-gauge transformation, of course, and which transforms both the energy momentum tensor and the spin tensor. And this is definition of Z, so nothing new here. And basically, the first thing is that when you change the I mean, you transform also the charge. The extra term that and the charge current. The extra term in the charge current is the divergence of an anti-symmetric tensor. So, according to Stokes' theorem, after integrating over this change only gives rise to a boundary term, and you can throw it away. I mean, if you can. And the other thing is that then you use this equation, solution for Z, and this shows you that the equations of motion remain the same under pseudo-gauge transformation. Basically, if you use the Pelifante pseudo-gauge, this guy goes to zero, and this becomes like trivial. But it's anti-symmetric in lambda and mu. Yeah. No, this. I mean, you need to use the. I mean, yeah, you need to use the Bianchi identity and then give it back to Z, and then you end up with this question. And actually, this is the These are the equations that are pseudo-gauge covariant. Otherwise, if you didn't have this term, you will end up with assuming that there is only one pseudo-gauge that uh, is valid, and that is very fun. Mm-hmm. Mm-hmm. First of all, I mean, the thing that will couple to gravity is not this energy momentum tensor. Yeah. As you already said, it's the Hilbert energy momentum tensor. Actually, I need to cheat here. The cheat is that if you think about everything in the semi-classical expansion, so this S actually doesn't exist at order h bar equal to 0. So then you are, in that sense, if you want to actually measure something, I mean, you are not in the classical theory anymore. That's also true. So yeah, basically you are asking that is there an experiment that I mean this kind of if you can do that experiment in the torsionless background, so it means that you can measure the pseudo gauge. Yeah, you can say that this is the correct pseudo gauge. Uh, I don't know the I mean I don't know the exact answer, but I think there shouldn't be. It shouldn't be possible because this is something that you can actually throw away with a pseudo gauge transformation. So yes. is issues, physical point of view, issues of molecule which can be. These are quantity removed by. It's something really, okay. Well, by the way, perhaps we can make this, say this now. We plan to have a discussion about the okay. We can let you go. Yeah, let me continue and then. Okay. So let's move on and just remind a few things about global thermodynamic equilibrium. This I'm just saying to clarify some notations. And first of all, I mean the Killing vectors that we have, all the Killing vectors that are in this particular space-time of interest, we can combine them with these guys. And what are these guys? These are the intensive parameters of the environment, which will be equal to the intensive parameters of the fluid or of the body when it is in global thermodynamic equilibrium. And we can make this so-called thermal Killing vector. And this thermal Killing vector should be time-like, but it's important not to confuse this with the beta vector. Yeah? So that is why the star is here. And of course, then I need to confuse you because actually in equilibrium, this thermal Killing vector is equal to beta vector. So it gives you the fluid velocity and temperature. It's just like a solution. It's just a coincidence at one point in the space of states of fluid. So, and then we will, I mean, since this guy is a Killing vector, so the symmetrization of gradients gives 0, but the antisymmetric part of the gradient is non-zero. And this is what you call thermal vorticity. Again, I put a star here because I want to avoid thermal vorticity out of equilibrium as far as I can. And the point here is that global thermodynamic equilibrium is dictated by the geometry of space-time and the intensive parameters of the environment. So these guys together, they give you the thermal Killing vector. Now, what happens in the so-called local thermodynamic equilibrium? I mean, we can think about local thermodynamic equilibrium, of course, as a state which each fluid cell is closed thermodynamic system. But I really don't like this picture, and I like this Israeli Stuart concept of local thermodynamic equilibrium as a map which maps each point in the space-time with a point in the set of all possible equilibrium states of the same fluid. And the thing is that, okay, you need to choose a u mu, which is something that Gabriel was talking about in more details. And then you use the matching condition here to find what is this epsilon here on this space. And then you find the hydrocurrents as expanding around this point. So around is a local expansion around global equilibrium. So this, if this map is unique, you can say that actually the fluid is in local thermodynamic equilibrium, which is only true for a perfect fluid. Now, when we get back, the thing is that this space is four-dimensional. Of course, if you have charge density, it becomes five-dimensional, so you have only epsilon and you have 3 degrees of freedom in U. But the thermal vorticity can also exist in global equilibrium, which means that it gives you 6 extra dimensions to this space. But if you have non-zero thermal vorticity in your reference equilibrium state, there will be some problems. And one problem is that you can see it from here. So in the usual power counting, in the gradient expansion, for example, which we say, okay, this guy looks like at first this is the acceleration, and this guy has only a first order derivative. But when you use the equations of motion, it is related to, it turns out to be second order unshell. Yeah. But you can see it here that there is a problem. And the problem is with this guy. This pi is the bulk, so it's first order. But how should we count A? Should we count it as zeros order or the first order? Of if you have thermal vorticity in your reference frame, so in your, I mean, your equilibrium frame, then this means that this guy can be first order. So then you cannot throw this away. And this means that you have an anisotropic equilibrium state that needs you to actually know everything from the build everything from the beginning. And to avoid this, okay, sorry, we will assume that actually thermal vorticity is first order in derivative. But we will remind ourselves always that thermal vorticity can exist in global thermodynamic equilibrium, so we need to take care of a few things for consistency. No, I'm not saying that I'm expanding in small gradients. Actually, I'm not doing gradient expansion. But if I want it, if I want to count the powers, I will say that, I mean, this will be important when we get to the spin potential. So we need to take the spin potential as something dissipative, not something that is. Yes. And this actually, I think is agrees with what Amos was telling us yesterday with some other problems. And uh, yes, but I will I will actually escape from this problem soon. Okay. So then, I mean, thermal vorticity actually is the intensive parameter for angular momentum in global thermodynamic equilibrium. This is something like chemical potential over temperature ratio being the related to the being the intensive parameter with respect to number density. But out of equilibrium, this is a dynamical variable. I mean, it's independent variable. We call it spin potential. And we believe that this is independent of pseudo gauge or things like that. So basically, this will be the thing that at the end of the day will be related to the observables. And as any ranked 2 antisymmetric tensor, it can be uh, decomposed into an electric component and to a magnetic component. And unfortunately, we have some signs that are not very nice. So this guy goes to minus acceleration over temperature, and this guy goes to, this is also a minus here, I missed, a minus fluid vorticity vector over temperature. I'm sorry for this strange letter here because I was out of omegas. Okay, so let's go to the more fun part with semi-classical spin hydrodynamics. So, I mean, what you want to do in principle is to just replace the usual standard model of heavy ion collisions with replacing hydrodynamics with a spin hydrodynamics. So you start with some pre-hydro tasks, you initiate at some point, very early time, the spin hydrodynamics now, which has some extra equations, and then at the end of the day, you should be able to calculate the polarization. But the semi-classical, this is actually very complicated because you have a lot of equations to solve, and each of these conservation equations, none of them are actually closed. So you will need extra equations. So this number of equations are not very nice to give to people. But the semi-classical expansion actually makes everything much easier. So we think that, okay, a spin is a quantum effect. So we use h bar as a power counting tool. So we expand everything in h bar. And this guy S uh, was the spin tensor, and we assume that the spin tensor is small. So we put an h bar already in this guy. And then this was our first assumption. The second assumption, we choose actually a pseudo gauge in only global thermodynamic equilibrium, the GLW pseudo gauge, that makes that eliminates the anti-symmetric part of T mu nu and mm, gives rise to S being conserved. But this is only in global equilibrium. And the last assumption that comes actually from quantum kinetic theory results is that any contribution to T mu nu only appears at second order H bar. So there is no first order H bar contribution to T mu nu. So with that, what happens is that there is no back reaction from a spin to the fluid. So basically, if you truncate the equations at first order H bar, you end up with d mu of the symmetric part of T mu nu being approximately 0. So you can use your standard hydrodynamics solutions and then put the results as an input to the spin dynamics. And here, this guy is second order H bar, so it means that this S is also, I mean, we had a calligraphic S. This is non-calligraphic S is also first order H bar. Okay. It seems very hard with this. Mm-hmm. You have an H bar squared here? Yes. It's just assumption that spin tensor is small. So you don't have a lot of, I mean, at the end of the day, the polarization is a small effect. It's not a, yeah. Sorry? Yes. 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 Yes, and this will actually haunt us at some point. I will show you. Yes. Okay. Mm-hmm. Yes, yes, I think that is true. But actually, the thing is that you are here doing something. I mean, imagine that we have chosen Bellefante gauge. Yeah. So then we would end up with this equation alone, and there was no equation of this sort. But actually, the problem would be that in that case, when you do this pseudo gauge transformation, there will be some physics that going from S and the antisymmetric of T inside the symmetric part of T. But that physics is second order H bar, and it's not easy to capture. So the point is that the problem, I mean, all of the setup is because if you use quantum kinetic theory and you want to, if you want to go to second order H bar, things will become not easy anymore. And basically, what you want to do, you want to extract an equation of motion for the spin potential from this guy. And in principle, it should be also derivable from uh, Bellefante. But that means that you need to know much more uh, that you already know. Yeah, you need to go to second order. If you're going to go to second order, you will see back reaction. And for example, if you I mean, there's something that actually appears in second order H bar anyway, is the coupling with electromagnetic fields and a spin that will produce a back reaction. This is also what you showed in that paper. So basically, uh, yeah, this is this will be the last part of my talk actually. Okay, this box is somehow lonely, but anyway, so we have 24 unknowns in this guy, and we have only 6 equations. So we want to define something. I mean, first of all, the other side, using the symmetries, we can write it in this way. So basically, this is based on the assumption that this vanishes in global equilibrium. And then for this side, of course, we have a z. I mean, you can call it zeros order, and you have a higher order. And here, the zeros order is actually not zeros order. I mean, it's first order in H bar and first order in derivative. And but the thing is that it only has 6 components. We assume this is the part with 6 components. So if you use only this part, then this equation will be close. So otherwise, for these guys, you will need extra equations of motion. And but this part is linear in the 6 components of omega mu nu, and we called it ideal dash spin, but it's a misleading term because it's dissipative. Okay. So again, using symmetry arguments, you can write this guy as this. So A, B, C, D, E are just some coefficients, which are functions of the fluid variables. And it turns out that if you want in global equilibrium that this guy be conserved by itself, these guys are not, this A and 2E are not independent, and you have to satisfy this equation. And nicely, this condition is satisfied by quantum kinetic theory transport coefficients. So, okay, I hope this is not you at this point. Okay, then you will have equations for these guys for kappa and omega instead of omega mu nu. And you can see that this is already an eastward-like equation. You have a time derivative here, and you have a time derivative here. And so the uh, the players here wants this inverse temperature derivative, and you have this expansion scalar, and you have the shear tensor, and you have the fluid vorticity, and so on and so forth. So actually what we need is just we need a solution to hydrodynamics to fit into the spin equations. And these equations are, as I said, are relaxation type equations, and they determine how the components of a spin potential relax to the components of thermal vorticity. And basically, before turning to numerical solutions, which solution already did, we can take a look into what is inside the poor man's toolbox, and we have the simple thing. It's hydrostatic, and then we have a linear hydrodynamics, and then we can have Bjorken flow. And let's first think about fluid equilibrium at rest. And okay, this is your fluid at rest, and you keep it at rest by you excite the spin. And the spin equations are quite simple here. And if you do a Fourier transform, what you find is that there are actually wave equations. They give you some damped waves, and this is the frequency of the wave now. And the damping term is determined by a combination of the two relaxation time for kappa and omega. And next you will say, okay, I will just try to be a bit more smarter and just perturb the fluid. And my naive expectation was that, okay, you will see some influence from the fluid waves to the spin waves. So this is the standard thing that we do with linear wave analysis, and we do the Fourier transform, and then the equations become like this. And then you write them in matrix form and try to find the characteristic equation. But it turns out actually that you can generally see that because of no back reaction from spin to fluid, there is no back reaction from the fluid waves to spin waves at first order in Schwarz. Because this matrix is block diagonal, and this is a general thing. It only needs you to truncate at first order in Schwarz. It doesn't matter how many degrees of freedom in your spin you have. So the spin and fluid mode decouple in the linear regime, and we end up with the same damped spin waves. Now let's do conformal Bjorken flow. Of course, Bjorken flow doesn't have thermal vorticity, but we do the same split as before. We start with, let's go on. Should I show it? The longitudinal waves actually do not propagate. You have only, yes. The transfers are the damped spin waves. They actually propagate by the damped. Speed is here. Some strange relation. Okay. Mm-hmm. Yeah. You can write it in thermodynamic way. I forgot to write it. Yes. Now for Bjorken flow, I like to do it with conformal symmetry, but I just do not use conformal symmetry for a spin because it actually is not does not work with what we have written. So we assume that conformal symmetry is a classical symmetry, so it's as O dash bar equal to 0, and then the Bjorken flow is determined by this form of T mu nu, and you will use the Miller coordinates. Then we use the DNMR equations of motion for the fluid sector, and we use the redefinition by Heller and Spalinski to write these equations as the first order nonlinear ordinary differential equation. And it's known that this has this attractor behavior in terms of W, the thermal time. And then for this F, we use a slow roll approximation. We put in this into the spin equations, and these equations give you this late time behavior. And this late time behavior is exactly what you asked. This is very similar to not very similar. This is exactly the behavior of the longitudinal waves. So it means that actually this this means that these relaxation times are not only damping the linear waves, but also the nonlinear Bjorken perturbations. Which one? This guy? Actually, by Bjorken symmetry, you can only have omega, and omega can only be have in the direction of eta. But yes, but if you are, you say, okay, I want to be demonstrative, you can use all of this, but all of them actually are the same. This is not a huge difference. And the thing is that these two, kappa and omega, will be decoupled. And okay, so of course you cannot calculate the term transport coefficient using hydrodynamics alone, and this is the relaxation times compared to the relaxation time for pi, which is calculated by David in terms of Z, which is mass over temperature. And as you see, the relaxation time for kappa and omega, both of them, are quite similar to the shear relaxation time for small z. But then for omega, you will see that it blows up when z gets large. So maybe you can interpret this as if you are in high energy collisions, then your spin potential relaxes very fast. But if you go to lower energies, and mass over temperature is large, then it might be the case that it takes a very long time for the magnetic component to relax. Uh, this is based on quantum kinetic theory. This calculation is quantum kinetic theory, but actually the thing is that you're comparing it with something with shear. So you try. We tried to do this just to make everything somehow. It's not model independent, but as much model independent as possible. This means that the relaxation time of spin, in a kinetic system, the relaxation time of the spin, the same order the relaxation time of momentum, up to some value of m. Yeah, exactly. So this means that if you are in go on. No, but I don't get the relation to low energy. Okay. You have a plasma there, yeah, if you have a lower energy, then means that what you have. You have a lower temperature. Not very low energy. You have lower temperature and you have more mass. Yes, yes. So basically, this is. This was before what these guys did. So this was a kind of prediction that actually the results from a spin hydro and your results should be actually very similar in this for 200 GeV. And but what might I will get to that point. It depends on which mass you make. Yes, but I mean, for this mass, you should take the something like 300 GeV, sorry, 300 MeV. Sorry, go on. Yes. Mhm. Yeah. Yeah, the solid lines for scalar four fermion interaction, the dashed lines for screen one gluon exchange. Yes. Yeah. Okay. I mean, that is a very good question that I don't have any answer, but I think, I mean, if you can actually find something about the polarization of an early time observable, something that comes from early times. Yeah, that's true. I mean, that is, wait, so maybe if you give me some time, I will show you a few things. I mean, do I have time at all? I mean, you can give me any time you want, but I don't want to be eaten by people. I mean, I have, I think, last 10 more slides, more than that. But I can show a few of them. I will be fast. Can I have 10 minutes or is it too much? Can I have 5 or 10? No, more. Okay. 15 minutes. 15 minutes, okay. So, okay, and this is the end of my fun part, which is the paper by David and Sushant, that these guys actually use this to use semi-classical spin hydrodynamics to calculate the polarization. I think, I don't know, Sushant is going to give a talk at some point. Okay, so this is just an advertisement. Okay, let's go to the price. So basically, I want to talk about a bit about thermodynamic stability here. And let's assume that we have a small body in some environment, some heat bath. And line shows the body state, and this is what we know about the body. And basically, we know that in equilibrium, the entropy is maximized. The only thing that we know is that the triply necessary knowledge, so of conserved charges. So this is the definition of equilibrium. So now let's assume that the environment performs some work to shift the system slightly out of equilibrium. And we know from textbook that the minimum work is given by this relation. And this is the temperature of the environment, this is the pressure of the environment, and blah, blah, and this should be positive. Now, if we take write this guys as first order derivatives, I mean the S as first order derivative with respect to E and with respect to V, and put this first order part to 0, we will find the standard thing that, okay, the intensive parameters, the temperature of the environment and the temperature of the body will be the same, and the pressure and also the same. And this can happen not only in this point, but it can also in this point, that there is no entropy produced, but the entropy is not maximized. So if you go away from that point, this turning point, you might gain some information or you might lose some information. And you don't know. And there are the second order derivatives of these guys that gives you the thermodynamic inequalities that determine that you're here or you're here. And these are basically the sense of the Gibbs stability criterion. And here you write this guy, this quantity, and this should be maximum in equilibrium. This is your knowledge, and this is the entropy. And you can write this as a flux, like this. And okay, what you want to do is to find the real maximum of this mu. And to do that, I mean, first of all, the relation for mu for this with anti-symmetric, sorry, with non-symmetric T mu is given by this. And this stars is again important because you never change these guys. These are your backgrounds. So then you slightly perturb the fields, whatever fields that you have. Here, for example, S, T, and S. In this way, you can define some parameter lambda, which gives you the state of the fluid. So lambda 0, arbitrarily we assume that this is the equilibrium state, and you can write the perturbations as like a derivative, a formal derivative with respect to lambda. And then at first order, if you solve this equation, you will find the stationary point conditions, which is basically saying that the beta star is equal to beta. And this guy should be equal to spin potential, and so on and so forth. And then when you go to second order, this is what Lorenzo calls the information current, can be built. And this guy should be future directed and non-space like. And from this, you will find a stability condition that tells you you're really here and not here. Okay, so one successful example uh, we did with Lorenzo, we applied this to what we call the Maxwell-Israeli sort. And I mean, the miracle part is what he called it. So you should blame him for a miracle. And the idea is that you have an Israeli star theory, and then you have also electromagnetic fields coupled to this Israeli star theory, and you don't care what is this Israeli star theory. And the only thing is that the entropy is exactly, I mean, the second law is exact as your order of truncation. Then applying this method, you will end up with understanding that the electromagnetic part of the information current is causal and stable by construction. So it doesn't change anything about the stability conditions that you already knew from Israeli Schwartz theory when you extend to magnet to hydrodynamics. Of course, you need to take care of the fact that now your chemical potential over temperature is related to the gauge field. But anyway, this was some kind of uh, advertisement. So now, how we can we apply this to our semi-classical spin hydrodynamics? So we know a few things at second order. We know this guy, and we know the anti-symmetry part of T mu. Okay, this guy is second order in H bar. This guy is second order, but actually there are some second order in H bar contributions to the symmetric part of T mu that we don't know. We never calculated. So this means that it means that we don't know everything that we need to find the stability conditions. And so to be consistent, we need to truncate second order terms and end up with this form, which gives you, the fluid stability criteria that you already knew. And also the important thing here is that we have escaped from many problems without knowing or without telling, with assuming that thermodynamic identities are also truncated. So you don't know what happens here in the Euler relation. I mean, what is the correction from a spin potential here? You don't, because this only appears at second order H bar, and it's not your concern. And to know this, and the thing is that there is, of course, you can write this guy as 1/2, I don't know, omega times S, but this is, I'm not sure if this is correct. I think Francesco has also some work on showing that this is not necessarily the case, that the entropy current is exactly what you expect from educated guess. But we have escaped from all of these problems using this H-bar expansion, but it will haunt us at some point. So it makes sense to go to secondary H-bar to know more things. Okay, now the question is that, is Francesco right or David? I mean, so it's the local thermodynamic equilibrium picture and the spin hydro. How do you compare them? I mean, it seems that when you're in high energy, they actually show the same result. Of course, this is not a solution to anything. This is some made-up picture. But the point here is that assume that you have some thermal vorticity, yeah, in equilibrium, or not in equilibrium, at uh, when spin hydrodynamics, let's lose this term, when a spin relaxes, spin potential relaxes. And it is for some components, yeah. But there are other components that should go to zero when relaxed. Now, if you are here, I mean, the consistency of the equations requires you to excite all of the components. So the components will be, there will be some transient components that will be eventually go to zero, and there will be some persistent components that will go to thermal vorticity. Now, if we don't have enough time and we calculate the polarization in some mid-time, then the components that that vanishes in equilibrium become finite in intermediate times. And basically, this means that if a spin hydrodynamics is true, then your polarization will have some components that you have never expected. So if we can do some kind of analysis like this, then we can decide if a spin hydrodynamics or any flavor of a spin hydrodynamics works better than the local thermodynamic equilibrium density operator and so on and so forth. And of course, a toy model, you can think about it, because I mean, actually, I was talking to Sushant, and Sushant actually told me that this is not very easy to do, to go to low energies, because we don't have a lot of hydrocoats that work well in low energies, and also we don't know equation of a state. A lot of problems, of course, but this is some funny kind of toy model. Because it's funny because it's a rigidly rotating cylinder, and of course there is no expansion, there is no shear, but there is rotation and acceleration. But the funny part is that it is hot outside and it's uh, cold inside. So if you think about it, you can think about, okay, I have a quark-gluon plasma here, and I have a hadron gas here. And yeah, it is funny, but then I excite the spin potential over this. And of course, at the end of the day, I know that the spin potential can only have two components. And one component is Z direction, and one component is R direction. But in the mid-times, all of the components get excited. So then maybe you can play the game with this to see what's going on here. So, and the question is, what is hiding at higher orders? I already said that coupling between gauge fields and spin degrees of freedom, that might be interesting or not, who knows? And anomalous transport effects. And also back reaction from a spin to fluids like Einstein-de-Haas effect. Also gravity-induced quantum effects that go back to all of this question that you were asking about this right-hand side of the mu nu. This is basically of second order H-bar, so you need to do some expansion second order, but and also if you use the quantum kinetic theory in curved space-time, you will see that everything that has a curvature comes with an H-bar squared, and this might be something interesting. I mean, of course, it's theoretically very interesting, but I don't know about the possible applications. And the other thing is that we would end up with finding an inherently anisotropic current in equilibrium. This is my summary, and I will not read. So thank you very much. One of the topics will be I think you're asking the wrong people. Mm. So I would also like, I mean, make your question, answer your question with by question, but almost that. Can you uh, really calculate the relaxation time for the shear from holography? But this is going, this is like, I mean, this is, I mean, what you actually calculate is a second order coefficient, but not necessarily relaxation time. That, yes, I understand, but I say that you do a gradient expansion. Yes, so you're assuming this is that. Mhm, mhm, mhm.